in USA. His Excellency Professor Alan Fryar from University of Kentucky, USA, the Honorable Lecturers of Water Resources Department of Universitas Brawijaya, and my beloved students and all distinguished participants at this 3-in-1 program. On behalf of University Brawijaya, I would like to welcome all participants to 3-in-1 program, visiting professor and guest lecturer by topic Groundwater Sustainable Development and Water Resources Management, hosted by Water Resources Engineering Department, Universitas Brawijaya. This guest lecture will be delivered by speakers from Department of Earth and Environmental Science, University of Kentucky, USA. We have an opportunity to learn from the expert, hydrogeology and groundwater. Ladies and gentlemen, as you know, hydrogeology and groundwater recharge and intersection with surface water is very important in water resources management. Therefore, it is important that hydrogeology and groundwater recharge need to be understood in groundwater sustainable development. I hope that through this program, we will get depth knowledge on how to develop groundwater sustainable development and water resources management. To our students, I really wish that you will get interesting knowledge. So you will take a huge benefit on attending this lecture. Finally, I would like to express our sincere gratitude and appreciation Prof. Alan Fryar for their valuable input to this program. I would like to congratulate and extend a special thanks to committee for their tremendous effort and support to organize this program successfully. Hopefully, this program will serve to broaden your perspective on groundwater sustainable development and water resources management. We also hope that in addition to this guest lecture, we can establish a cooperation in other programs such as collaboration research and exchange student. We hope to. Thank you. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Terima kasih Ibu Dr. Usi Ondawayanti. Thank you very much to welcoming speech today. And ladies and gentlemen, according to our schedule, we are going to continue the presentation and discussion from Prof. Alan Fryar that will guide by our moderator today, Mr. Jetvan Sidki Vidari. Time is yours, please.
Thank you, Ms. Assalamualaikum warahmatullahi wabarakatuh. Good everyone and evening, Prof. Alan. Everyone here.
Mr. Jetvan, are you okay? Maybe that you have a trouble with your signal? Mr. Jetvan? Yeah. So, Mr. Jetvan, can you stay in this Zoom?
Maybe it's trouble.
Maybe Mr. Jetvan a little bit trouble today. So Professor Alan maybe can he's come back. So please, Mr. Jetvan.
Is anyone can voice?
Your voice is
Okay.
blank.
Not stable, Pak Jadvan.
The problem with the online course is
Yeah.
also the signal. So
That's-
sorry.
I have
No.
a problem.
Yeah, good.
I'm sorry. I have problem with my connection. Is that clear, my voice?
Yes, it's great, but maybe your
Yeah,
bandwidth is
Jadvan,
better.
maybe if you turn off your video
Yeah.
and just go to audio.
Okay, I will do that. I'm sorry regarding the internet connection problem. Good morning, everyone, and good evening, Professor Alan and also Professor Carmen. Today I will give a brief introduction about Professor Alan Vite. Professor Alan is have a lot of experience in groundwater and research about groundwater flow and geology. He finished his PhD in University of Alberta, Canada in 1992. He have a lot expertise is modeling studies of groundwater flow, mass transport, and reaction of subsurface. And he has also a lot of research and papers regarding his research. Maybe if you want to know and further about Professor Alan, you can search in Google Scholar to know about his paper. And I will not hold any longer about this moment. Maybe we can continue to Professor Alan to deliver his lecturing this morning. Professor Alan, times and floor is yours.
Okay, Jadvan. Terima kasih. Assalamualaikum. And Bu, Dr. Usi, and colleagues, thank you for hosting me for this wonderful opportunity and this great introduction. As I was mentioning before we started, when I was talking with Jadvan and some of the other participants, I have wonderful memories of the 2 weeks that Adam and Carmen and I spent with colleagues in Indonesia at IPB and at Brawijaya in June of 2013. And I am delighted to make connections again with you. I am also pleased that Adam and Carmen were willing to participate again because of their expertise that is beyond mine in things certainly like remote sensing, for example, and stream restoration, which Carmen will be talking about. I am a hydrogeologist by training. All of my degrees are in geology, although I have taken some classes in engineering and have been collaborating with engineers and with people in agriculture for the past more than 25 years. But what I'm going to be doing today is beginning with an introduction to hydrogeology. And I realize because of the range of people attending, I gather some are students, some are research scholars, others are professors or lecturers. And so people will have a range of backgrounds. And so some people may be more familiar with what I am talking about than other people. Also, because of the schedule, because Adam gave the first 2 lectures, I realized that he may have introduced some of this material. So again, some of this may be review, but I will try to move through things systematically. And I would encourage you to ask me any questions or put questions in the chat if you wish. This is the first of 3 lectures I'm going to be giving. Tomorrow, I will be talking about groundwater recharge and groundwater interactions with surface water. And then next week, I will give the first lecture on groundwater geochemistry and contamination before Dr. Carmen Agaritas gives the final lecture. So with that, I will go ahead and share my screen. Let me go ahead and open my PowerPoint lecture here. And I will see if I can find this. Bear with me just a moment. All right, so hopefully all of you can see this, and I'm going to put it in as large as possible. So can everybody tell me, is this visible? Boozy, can you see this okay? Or okay, people are
Yeah.
nodding and thumbs up. Good, thank you.
Yeah, thank you.
All right.
Good.
So what I'm going to do then is just start by talking about what hydrogeology is. And this may seem a little bit simple, but I want to kind of provide my perspective in terms of a geologist. So I focus on study of water in the subsurface, primarily groundwater, so water in the saturated zone. And so that leads to the question, what is groundwater, which is probably obvious. As I mentioned, it is focusing on the saturated zone where all the pores are water filled. So then we could ask the question, why do we care about groundwater? And obviously groundwater has multiple uses. Groundwater is a resource for obviously public water supply, for irrigation and livestock watering and other agricultural sources, for industry, for mining, as well for engineers. Control of groundwater can be important in terms of controlling excavations. And as I'll talk about next week, groundwater contamination can pose a public health hazard as well. So there are multiple reasons that we study groundwater. As a resource, groundwater is the vast majority of available fresh water on Earth. By available, I am not including the polar ice caps and the snowfields and polar regions, which are the largest single source of fresh water on Earth. Groundwater is liquid, obviously. Groundwater is important in part from an ecological perspective, as well as for surface water hydrology as well, because groundwater can sustain stream flow during dry periods. It provides base flow. And so I will be talking more about that in my next lecture. I'll also be talking about different types of aquifers, which are geologic units, sediments or rocks that can yield water to wells or to springs. And again, I'll be talking more about springs next class. So this is just a schematic from the US Geological Survey showing the distribution of water on Earth. And again, you're probably familiar with this. The oceans are about 3/4 of Earth's surface area, but almost 97% of Earth's water. Fresh water is only 2.5%. Of that 2.5%, about 2/3 is as glacial ice and as ice caps. And most of the remaining 1/3 is as groundwater. And you can see that surface water and other fresh water are only about 1.2% of the fresh water on Earth. You're no doubt familiar with the aspects of the water cycle. I won't be talking about all of these in my lectures, but I will be focusing on aspects such as infiltration, groundwater flow and storage, groundwater discharge, stream flow, evapotranspiration, and precipitation. So this is a diagram from the textbook that I have used most recently for my hydrogeology class, which is taken by both upper level undergraduates and graduate students from different fields at our university. So I'm going to draw a distinction between not simply the unsaturated and saturated zones, but actually the vadose zone. The idea being that the vadose zone is where pressure is less than atmospheric. In general, there are exceptions. We can have so-called perched aquifers We can have wetting fronts moving through the vadose zone. So there can be zones of temporary or discontinuous saturation
Mr. Alan,
above.
I'm
Yes,
sorry
sir.
interrupting. Could you make your presentation more bigger? Because
Yes,
some of
absolutely.
students cannot see it clearly.
Okay, is that better?
Thank you. Better. Good.
Okay, good.
Thank you.
Yes, no problem. Okay, so back to the diagrams here then. So we can draw the distinction between the vadose zone and the saturated zone. The terms vadose and unsaturated are often used interchangeably, but part of the difference is that the capillary fringe, or the zone of capillary uptake above the water table, which is marked with this inverted triangle, is actually considered part of the vadose zone, but it is where water is saturated, but at pressures less than atmospheric or under tension. So the unsaturated zone technically starts at the top of the capillary fringe, whereas the vadose zone includes the capillary fringe. You'll sometimes hear the saturated zone where groundwater occurs called the phreatic zone as well. So again, pore water pressure is referenced to atmospheric, and it is less than atmospheric or less than zero above the water table, but it is only above the capillary fringe that the pores are not fully water saturated. And again, there are exceptions to that rule because we can have zones of discontinuous or temporary saturation above the capillary fringe. So just from a volumetric perspective, we can talk about porous media as being soil or sediment or rock. And we can define the total volume of porous media as consisting of the volume of voids or the volume of holes, and then the volume of solids. And the volume of voids in turn can consist of the volume of liquid and the volume of gas. And so in the vadose zone, we can define the volume of liquid as being the volume of water and the volume of gas as being the volume of air. And we will abbreviate these as VW and VA for the volume of water and the volume of air. And then, of course, in the saturated zone, the volume of voids, abbreviated VV, is equal to the volume of water. That is, all the pores are filled with water. So this diagram simply shows in granular media like soil or sediment or sandstone that in unsaturated conditions that water occurs as pendular rings. That is, water is bonded by hydrogen bonding, by capillary attraction to the mineral grains, but there are pockets of air, the so-called non-wetting fluid, also in the pore space. So again, this is representing the vadose zone. So we can define related variables. Obviously, porosity is the ratio of the volume of voids to the total volume, or written another way, it is the difference between the total volume and the volume of solids divided by the total volume. And we discuss this or represent it either as a percentage or as a decimal. So less than 1 or less than 100%. We can define the volumetric water content as the volume of water divided by the total volume, and that just equals the porosity in the saturated zone. We can also define the gravimetric moisture content, so with a G subscript instead of a V subscript for volumetric moisture content. The gravimetric moisture content is just the ratio of the mass of water to the mass of solids. And we also can define the bulk density as the ratio of the mass of solids to the total volume. The solid density is the ratio of the mass of solids to the volume of solids. And these various relationships can be rearranged. So porosity, for example, can be defined in terms of the bulk density and the solid density. In the absence of information about mineralogy, we commonly assume that the solid density is the value for quartz, because quartz is perhaps the most common mineral in soils and sediments, about 2.65 grams per cubic centimeter. So from a geologic perspective, we can talk about types of porosity in terms of how porosity formed. And this gives us insights into how well connected the porosity may be. So this includes primary porosity created at the time of deposition or crystallization of porous media. So when we talk about deposition, we're talking about sediments, for example, like sand or silt or clay. In terms of crystallization, we may be talking about sedimentary rocks such as limestone. Secondary porosity is porosity that's created by processes such as jointing or fracturing, by faulting, and by weathering, which can include either the mechanical breakdown of the rock or soil, or it can include the dissolution of soluble components, or both. And finally, we can define the effective porosity. And this is really the porosity that is available for flow. It is the ratio of the interconnected volume of voids or pores to the total volume of porous media. So the effective porosity is typically less than, but cannot be greater than the total porosity in. So I'm going to show you examples of 3 different types of rocks. I'm not sure how many of you have had classes in geology previously, either at the secondary level or in university, but sandstone is simply a sedimentary rock where there are grains of sand that are cemented together by other minerals. Limestone is a sedimentary rock made from calcium carbonate, either precipitated from seawater or sometimes lake water, or sometimes formed by shells being cemented together. And then basalt, you are probably familiar with, being in Indonesia, which is volcanic terrain. Basalt, of course, is what we call an extrusive igneous rock. It forms from the cooling of lava that has been erupted. So if you look at these 3 different types of rocks, what can you tell me about the different types of porosity, whether it has primary porosity or secondary porosity, and which of these rocks do you think has the highest effective porosity? That is, which rock has the most interconnected pores? So if you want to take a minute to just think about this, or to chat with each other, go ahead and do that. And then perhaps someone can put in the chat or can speak as to which type of porosity they think is associated with each of these rocks and why.
Anyone? Or still discussion with other, I think, for sure.
And you're welcome to chat with each other. I tell the students in my class when I was teaching on Zoom last year, I am perfectly happy to wait. And I realize that sometimes participants are shy. So there are no wrong answers. I'm happy to hear your guesses. Okay, I see a comment in the chat. Okay, Faisal, not a geologist by training, but limestone has the highest porosity among the 3. And then David says limestone has the most porosity. Do other people think that way too? Let's give it another,
Maybe they still typing.
Oh, okay, no problem.
Maybe.
And I realize
1 or 2 minutes.
Yep. And of course, I am speaking in English. I'm trying to speak slowly.
No, I'm just joined to the.
So I know your English is much better than my Bahasa. So
Please, if you want to answer the question from Professor Alan, you can type it or just direct deliver your answer.
Okay, Jadfan, should I continue?
Please, continue. Maybe
Okay,
they still
all right.
not awake
Well,
enough.
and feel free to put comments in. All right, a couple of people are saying sandstone. So both of those are good guesses. And my answer is a bit of a wiggle. I would say it depends, that you can't always say that limestone has greater porosity than sandstone or vice versa. It's interesting that nobody said basalt. I suspect in this case, the limestone probably at least has greater effective porosity because the porosity in limestone is secondary porosity. When we talk about weathering, weathering can either create porosity or it can destroy porosity. So sandstone, I'm looking at Dion's comment, is the highest porosity because it has the highest fraction of void space. That is true for sand, but once you start to cement the sandstone, in this case, it's probably iron oxide that is filling the pores, that's holding the sand together, that is going to reduce the porosity, that will reduce the amount of open pore space. So in this case, this porosity is being lowered by weathering, by precipitation. And in the case of limestone, the porosity is being increased by weathering, by dissolution, because limestone is calcium carbonate and it dissolves fairly easily in rainwater, which is mildly acidic, pH about 5.5. So we will talk more about that tomorrow. Basalt is an interesting case. The holes in the basalt probably came from gas coming out of the lava as it was cooling. And so the basalt may have significant pore space, but it probably doesn't have many interconnected pores. So I think that the limestone is probably greatest. Maybe the basalt is in the middle and the sandstone is lowest in this case, but you can't generalize for all sandstone, all limestone, and all basalt. It depends upon the local geologic conditions. Sometimes, for example, the basalt is fractured, and if there are fractures in the basalt, then water can move more easily. So it's kind of a, not quite a trick answer, but my answer would be that it depends on the local geologic conditions. But in this case, I think the limestone probably has at least the most effective porosity. Okay, good. So let me keep moving then. So let me talk a little bit more about porosity. If we talk about intergranular, meaning porosity between the grains, like the diagram that I showed, the amount of intergranular porosity is going to depend on the packing and how compacted the grains are, how much they're squished together. It's going to depend on the shape of the grains. How spherical are they? And it's kind of an interesting trick, but from first principles from geometry, if you have grains that are perfect spheres, obviously that's a simplification. Grains usually aren't perfect spheres, but if you had perfect spheres and they were all the same size, if they are all packed the same way, it doesn't matter what size they are. If the grains are all spheres that are packed the same way and they are 1 centimeter diameter, then the porosity will be the same as if they were 1 millimeter diameter. But we know, of course, with real soils and real sediments and real sedimentary rocks, that the grains are not all the same size and they're not all the same shape. And in fact, you can have small grains in between big grains. And that relates to particle size distribution. For those of you who, for example, may have had soil mechanics, you may be familiar with the concept of sorting versus grading, that if sediment is well sorted, it's all about the same size. Whereas sediment is poorly sorted or well graded, you may have a broad grain size distribution. And then I just talked about weathering. Diagenesis is a geological term. You may be familiar with metamorphism, which is the alteration of rock under pressure and temperature, or sediment under pressure and temperature when it's buried. So weathering occurs at temperature and pressure close to Earth's surface conditions. Diagenesis occurs at slightly higher temperatures and pressures, burial depths of perhaps several kilometers and temperatures of perhaps 150 degrees Celsius. And then above that is metamorphism. So the bottom line is, if you have well-sorted, relatively coarse grained sediment or soil like sands, then it will have relatively high porosity and relatively high effective porosity. But as it is buried, as it is cemented, that will reduce the porosity. If it becomes a rock and then the rock starts to dissolve, then that will start to increase the porosity. Also, if the rock is fractured in some way, that can increase the porosity. So our total range of porosity ranges from a little bit above zero. Even at the atomic level, you can have pores, you can have micropores. So it's really tough to find something that's zero porosity, but you can find something with porosity much less than 1%. It will go up to about 60%, so maybe 2 to 3 orders of magnitude. And it's typically much higher for soil or sediment than for rock because the pores are open in soil or sediment. So this is just a schematic I drew showing loading, and then if there is compaction by either burial naturally or by building structures, for example, or rolling a sheep's foot roller, if you're building a highway, that will reduce the porosity, and then cementation will plug the pores further. So let me pause for a moment and see if there are any questions before I continue. Okay, again, if you have any questions, please put them in the chat or just speak out loud. We can talk about different types of aquifers. I mentioned that an aquifer is just a layer of rock or soil or sediment that can yield water to a spring or a well. An unconfined aquifer is the type of situation I showed in that first diagram, where the water table forms the upper surface. By comparison, a confined aquifer is deeper in the saturated zone. It lies below what we call a confining layer. Sometimes we use the term aquitard, and that is a zone of rock or sediment that limits the flow of groundwater. We use the term permeability. I will talk more about that later. Permeability is related to effective porosity. That is, it is a measure of how easily water can flow through the rock or the sediment. And so confining layers tend to have low porosity, certainly low effective porosity, and low permeability. Back to the special case that I talked about with the vadose zone, where you can have discontinuous zones of saturation within the vadose zone, you can have what we call perched aquifers. And for those of you who are familiar with soil science or with agricultural engineering, you may be familiar with, for example, plow pans or soil crews, where you have a relatively low permeability layer, but it is above the water table. And so what can happen is water can infiltrate and mound on that perched aquifer. So it is a discontinuous zone of saturation within the water table. So you can either have a confining layer within the saturated zone under a water table or unconfined aquifer and above a confined aquifer, or you can have a confining layer in the vadose zone and beneath it is unsaturated and above it is a perched aquifer. And finally, back to the case of the saturated zone, you can have an artesian aquifer, which is where the water level is rising in a pipe above the top of the aquifer. And we typically think of artesian aquifers as being confined, but you can have artesian conditions where groundwater discharges from an unconfined aquifer. And I will talk more about that tomorrow. So this is just a schematic from the National Groundwater Association, which is one of the professional organizations I belong to. And this shows these different types of aquifers that you start at land surface, and then going below land surface, you may encounter a confining unit, a low permeability unit like a clay in the vadose, and that creates a perched aquifer, which is a type of water table aquifer. And then you hit the main water table, which is the top of the zone of saturation. That's the unconfined aquifer. And then there is a confining unit beneath it. And then below that is a confined aquifer. Also note the term recharge area and water table. Again, the water table is the top of the saturated zone. And the potentiometric surface, which is the height that water will rise from a confined aquifer for artesian conditions. So I will show examples, more examples of all of these later. So a key parameter in hydrogeology is the hydraulic head, which is just the height to which water rises in a well. So dimensionally, we're just talking about dimensions of length, like meters. And the hydraulic head can be divided into two main components. And this relates to Bernoulli's equation in part. I'm not going to get into the fluid dynamics here. I'm certainly not a fluid dynamics or fluid mechanics expert. But these two main components are the elevation head. And we define this as Z or Z, which is the height of the elevation at the intake, that is where the water is coming into the well. And so I will go back up to the previous slide. So these horizontal lines here represent what we call a well screen, that is perforated or slotted pipe, and water flows into these holes in the pipe. And so the intake would be relative to some datum like sea level. And in this case, because the intake is not just a point, but extends over a certain length of the pipe, we would pick the intake as the middle of this screened or perforated interval. And then the height of the water column above the intake we define as the Greek letter psi, which is the ratio of the fluid pressure to the unit weight of water, the product of the density of water times the acceleration due to gravity. And we define that product as gamma. So going back again to the previous diagram, the pressure head for this flowing artesian well would be the height of the water column above the midpoint of this perforated or screened interval, above the intake. And when we are talking about groundwater flow, we are not talking about hydrostatic conditions typically. Hydrostatic conditions would be for, in effect, a closed system like a container of water. And under those conditions, the hydraulic head is constant because the elevation head increases, the pressure head rather increases as the elevation head decreases. So I will show hydrostatic conditions in a minute, but I wanted to show another schematic with the hydraulic head here. And in this schematic, we're just assuming that this is a pipe or a boring, like a dug well in the ground where it's just open at the bottom to groundwater. So this is maybe easier to visualize as your intake, just a point. And this is your datum. So your elevation head is defined as Z, and it's the height above that datum where the intake is, in this case, the bottom of the well. And then the pressure head is defined as psi. And then the hydraulic head, or sometimes called the total head, is just the sum of Z plus psi. So I'm going to pause again for another question here. I won't take as long. I will take perhaps a minute. But how would you calculate the hydraulic head if you don't know the elevation of the intake? What would you need to know to calculate the hydraulic head in this well, the water level relative to the datum, how would you measure it? Say you have a well, you're out in the countryside, like in a rice paddy, and you come upon a well. What would you need to know to define the elevation of the water in that well above sea level? The reason I'm asking this is when we map groundwater, when we map the water table, for example, typically we're mapping elevations. So how would you figure out the elevation of the water in the well? Okay, I'm seeing the chat. Faisal, okay, good man. Measuring tape and a handheld GPS. Okay, Faisal, what does the handheld GPS give you?
The ground elevation.
Exactly. It used to be that we might be in the field with a topographic map, for example. But if the handheld GPS is high enough accuracy, then you can use the handheld GPS for local elevation. And then the measuring tape just gives you the depth to water. So if you have the land surface elevation minus the depth to water, that gives you the hydraulic head. And then if you want to know the components of the hydraulic head, you have to know where the intake is located. So in this case, if it's just the bottom of the well that is open, that is the intake, then if you have a measuring tape or like a piece of rope with a rock on the end, and you know the total depth of the well, and you know the depth to water, then the pressure head is just the difference between the depth to water and the total depth of the well. And then the elevation head, because you've already figured out the hydraulic head just by knowing H equals Z plus psi. Good. Okay. So in terms of hydrostatic conditions, pardon me, let me go back to the previous slide. This just shows hydrostatic conditions that in a closed water column, your hydraulic head or your total hydraulic head is constant, and the pressure head increases with decreasing elevation, and your elevation head decreases, and they cancel each other out. Again, we typically don't worry about hydrostatic conditions in the field, except when we are looking at the hydraulic head of a surface water body. For example, a lake. If you are looking at the hydraulic head of a lake, then the hydraulic head is referenced to the bottom of that lake, that the elevation head balances out the pressure head within the surface water column. And we will talk more about that tomorrow when we talk about groundwater interactions with surface water. So this leads us to the hydraulic gradient, which is just the difference between the hydraulic head measured at 2 points divided by the distance between those 2 points. And we will sometimes call the hydraulic head little or lowercase I. And of course, the difference between these two quantities, we can just write shorthand or abbreviate as delta. So we call this delta H. And the denominator, the distance between the points, you will see written as L or sometimes as delta L, but this is dimensionless. It's dimensions of length in the numerator, length in the denominator. Note also that it doesn't really matter whether H1 is your upstream or up gradient point, or whether you call that point H2. So sometimes you will see this written as H2 minus H1 over L, or H2 minus H1 over delta L. But really what you're just concerned about is the difference in hydraulic head. And you need to know which point is up gradient or up the flow line, and which point is down gradient. Hydraulic head is really the driving force for groundwater movement. And an easy way to think about this is a bit of a simplification, but it works pretty well, is you can think of the hydraulic gradient as the slope on the water table for an unconfined aquifer, if you were assuming horizontal flow. So this is your next opportunity, and I want people to work on this for a couple of minutes to calculate the horizontal hydraulic gradient. So you were given two wells here. Faisal Roma told you how to calculate the hydraulic head in the well, and then you were given the distance between these 2 points. So again, feel free to work on your own, feel free to chat with other people, but take about 2 minutes and calculate the hydraulic gradient in this case. And as soon as you think you have the answer, let me know, and I will wait a few seconds and then we will talk about it. Okay, so I see a couple of answers from Dian and Judpan, and I see David. Okay, does anybody else have a different answer? Does everybody agree with this? Okay, Rizky. Rizky's got it. Can you explain why?
I think because it has elevation, so we need to calculate the elevation first before we calculate the difference of headless.
Excellent. So the difference in hydraulic head, the head loss, is has to account for the difference in elevation. So the hydraulic head at the first point is 100 minus 15 or 85 meters. And the hydraulic head at the second point is 98 minus 18 or 80 meters. So the answer is indeed 85 minus 80 or 5 divided by 780, which is 0.0064. Good, good. Thank you all for giving your answers. This is actually a question that I give my students in class too. Okay, so we've talked about the horizontal hydraulic gradient, but we can also talk about the vertical hydraulic gradient if groundwater flow is predominantly upward or downward. And so here I will use the Z subscript to indicate the vertical coordinate if the hydraulic gradient is dominantly vertical. So in this case, which direction is groundwater flowing? Again, this is a question that I ask my students in class. Okay, David says left to right. And David, that's what my students say all the time. So you are in good company with them. But Faisal actually has it. It's downward because we're talking about vertical conditions, vertical hydraulic gradient rather than horizontal. So these wells are very closely spaced next to each other. So often my drawings are not to scale, but in this case, it's pretty close to scale. If you look at the tree and the size of the tree, maybe these wells are just a meter apart. So this is what we would call a nest of monitoring wells. So in fact, flow here, if these were farther spaced out, like the previous example, then flow would be left to right. But in this case, flow is downward from higher hydraulic head to lower hydraulic head. But if the well at the left was deeper, then flow would actually be upward. So you can have an upward hydraulic gradient in the discharge zone and a downward hydraulic gradient in the recharge zone. And you may say, well, how can groundwater flow up? How can it flow opposite to gravity? And the answer is that the pressure gradient, the pressure component of the hydraulic head, is greater than the elevation gradient. So the pressure gradient is overcoming gravity. And that's why we see, for example, springs with water flowing upward. Okay, very good. All right, the next variable I want to talk about is hydraulic conductivity. And I used the term permeability before. Hydraulic conductivity is specific to water. So it is a measure of how permeable porous media, type of soil or sediment or rock, is specifically to water. And the hydraulic conductivity is defined as capital K and is equal to this right-hand relationship, the product in the numerator K, which is what we call the intrinsic permeability of porous media to any fluid. And that's actually in dimensions of length squared. And I don't think Brawijaya has a petroleum engineering program, but I know that petroleum is a very big industry still in Indonesia. And petroleum engineers tend to talk more about permeability because they're looking at other fluids. They're looking at liquid hydrocarbons or natural gas, and they're often looking at multi-phase flow, not just liquid or even liquid and air, but liquid hydrocarbons and liquid water and natural gas. So they tend to think about permeability because they're looking at different fluids. But we as hydrogeologists typically just talk about water. And so we use this term hydraulic conductivity, again, which is the product of the permeability for any fluid for that type of rock or soil or sediment, times the density of water, times the acceleration due to gravity, all of that divided by the viscosity of water. So when we talk about hydraulic conductivity obviously depends on permeability, but it also depends in some way on porosity. And that dependency is difficult to define unless you're talking about very simple idealized geometries of packed spheres or parallel tubes, in part because, as I mentioned, in real soil or sediment or rock, not all the pores are open to flow. Some of them are going to be disconnected, perhaps, or dead-end pores. So it's difficult to establish from first principles a theoretical relationship between porosity and hydraulic conductivity. It's really more a dependency between effective porosity and hydraulic conductivity. But in any case, whether we're talking about hydraulic conductivity or permeability or porosity, they typically vary depending upon the scale. If you think back about that diagram that I showed fairly early with the grains and the pore partly filled with water, partly filled with air, if you zoom in to a small enough scale, then you will have effectively a permeability or a porosity of almost zero because it's all solid. if you zoom in at that same scale in a different location, it may be close to 100% porosity and very high permeability or hydraulic conductivity because it's a hole. But as you zoom out, you are sampling at a larger volume a mix of solids and holes. And so that's going to vary depending upon your sample volume or sample size. So that then kind of leads to the question, how do you measure hydraulic conductivity? So I mentioned there are empirical correlations with porosity or for granular media with the diameter of the grains. At the laboratory or outcrop scale, you can also use something called a permeameter, which is a means of passing fluid through the rock or the soil or the sediment at a known rate. And then you can calculate the hydraulic conductivity. What we as hydrogeologists and as water resource engineers often do, and I'll talk about this a little bit, but not much later, is at the field scale, what we call hydraulic tests, like pumping tests or slug tests. You may have heard of specific capacity or well yield tests. Hydraulic tests are a particular type of test where you pump at a known rate, a known volume per time, and you monitor the change in the water levels in the well, or you displace the water in the well with air, or with a solid, what we call a slug, a piece of solid pipe, and then you monitor how the water level changes after you do that. And again, you can calculate the hydraulic conductivity based on that. So when I talked about porosity, I said the range of porosity values was from less than 0 to 60%. And I also just said that the hydraulic conductivity varies non-linearly with porosity. It's really a function of effective porosity, which can be difficult to measure. But hydraulic conductivity values, because of this non-linear dependency, occur over a much, much broader range than porosity. So porosity may be over 3 or 4 orders of magnitude. Hydraulic conductivity ranges over 12 orders of magnitude, from about 10 to the minus 14 meters per second to about 10 to the minus 2 meters per second. So we can ask what type of rocks and sediments are likely to be aquifers and what types are likely to be confining units. That brings us to this next diagram, which is from the textbook again by Fitz, which shows typical values of hydraulic conductivity in meters per day and centimeters per second. So the lowest values for rocks tend to be for shale or claystone and for igneous and metamorphic rocks. And so those are more likely to be, at least in the case of shales, confining units, because you have layers of shale interbedded with layers of other sedimentary rocks. If you have unfractured igneous or metamorphic rock, you don't really talk about a confining unit as much as you just talk about really low permeability rock. It's not going to be a very effective aquifer unless it's fractured. But as you start to look at sandstone, it has higher hydraulic conductivity. It's more permeable. And then limestone overlaps with that, and then fractured basalt overlaps with that. So these are the 3 types of rocks I showed in the slide before. And then if you're talking about unlithified material, that is sediment or soil, the lowest is clay, and then glacial till in areas that have been glaciated. I know there aren't many glaciers in Indonesia, but I know in Irian Jaya, there were glaciers, at least until recently, in some of the high mountains. So glacial till tends to have a high percentage of clay, and clay can be high porosity, but the pores are very small and not very well connected. So it's low hydraulic conductivity. And then as you increase grain size from there, as you go to silt and silty sand and clean sand and gravel, you increase the hydraulic conductivity. So maybe sandstone, limestone or dolomite, fractured basalt, sands and gravels tend to be good aquifers, and clay and glacial till and shale tend to be confining units. All right, one last thing to note about hydraulic conductivity, and this kind of gets at what I was talking about with the hydraulic gradient. calculating the horizontal hydraulic gradient or the vertical hydraulic gradient is groundwater flows in 3D in the real world. It flows vertically, it flows horizontally in the longitudinal direction and the transverse direction. There may be a preferential direction of groundwater flow. In fact, you can do vector resolution on a map of hydraulic heads to determine the dominant direction of groundwater flow. But groundwater doesn't just flow typically in the X direction horizontally or in a Y direction or just vertically in the Z direction, even though it may dominantly flow in one of those directions. It doesn't exclusively flow. Well, likewise, hydraulic conductivity can vary with direction. And part of this is, if you think about it, related to the physical texture of the material you're looking at. If you think of sand, or if you think of clay or silt or basalt as cooled lava, it tends to be laid down in layers. And so there may be preferential orientations of what we call the fabric, the layering. That means that you have a higher hydraulic conductivity in one direction than you do in another. Usually we assume the hydraulic conductivity is higher horizontally than it is vertically. But we can start out at a point by saying, well, we may assume that the hydraulic conductivity is the same in all three directions. Well, the counter to that is to say, well, maybe the hydraulic conductivity is the same in two directions, but not in the third at a point. Or maybe it's different in all three directions. Likewise, if we're talking about 2 points in space, maybe we can say the hydraulic conductivity in one direction, say the horizontal direction X, is the same between these 2 points. And maybe we can say the hydraulic conductivity perpendicular to that horizontally is the same between the 2 points. And then the hydraulic conductivity vertically is the same between the 2 points. So isotropy says at one point, the hydraulic conductivity is the same in all three directions. Homogeneity says for 2 points in any given direction, the hydraulic conductivity is going to be the same, X to X or Y to Y or Z to Z. Well, in the real world, typically hydraulic conductivity varies at a point and it varies between points. And so for a lot of the derivations that we do, like solving the results of pumping tests, we assume hydraulic conductivity is constant in space. But realistically, we know that that's not necessarily true. And typically the best case is that maybe it's the same at a point, but it's different between points. So maybe it's isotropic, but heterogeneous. But really, we assume the simplest case that it's constant in space. And in fact, it may be variable at any point in different directions or between points. So that's what happens when you deal with the real world, with real soils or sediments or rocks. So this gets me to bringing together all these different pieces, the hydraulic head, the hydraulic gradient, the hydraulic conductivity. And I do this to answer the basic question, how do you relate the groundwater flow, the volume flow rate per time, or the volume flow rate per time divided by the area through which the water is flowing, to the water levels along the flow path. So this is what we call Darcy's law, where big Q is the volume flow rate per time, dimensions of length cubed per time, and A is the cross-sectional area, and that ratio, capital Q over capital A, we define as small q, and that equals the hydraulic conductivity times the hydraulic gradient. So basically, the hydraulic conductivity is a proportionality constant that relates the groundwater flux to the hydraulic gradient. And we call this little q the so-called Darcy velocity, or the specific discharge. It's the groundwater flux, its dimensions of length per time, but it is greater than, it is less than the true velocity. The groundwater flux is less than the true velocity. And the reason why is if you divide the volumetric flow rate by the cross-sectional area, if you think of a pipe packed full of sand, so that your cross-sectional area is the circle, the circular cross-section of that pipe, and water is flowing normal to that circular cross-section, water is not able to flow through the entire cross-sectional area like in open channel hydraulics. It's only able to flow through the holes. So the cross-sectional area that's available to flow is the effective porosity, or sometimes we just assume porosity, times the cross-sectional area. So the true velocity is this groundwater flux, little q, divided by the porosity, the effective porosity. And so the example that I use here is like a garden hose. My house, we have a big backyard and we have a vegetable garden. And if I want to water my plants and I open the tap and the water comes out the hose, what happens when I squeeze that hose? The water comes out faster, right? And it's because I am maintaining a constant volume rate of flow, but I am reducing the cross-sectional area. So if you reduce the cross-sectional area, you have to increase the velocity. So basically, again, the area that is open to flow through which groundwater is flowing, like across the cross-section of an aquifer, is the product of the porosity or the effective porosity times that cross-sectional area. It's going to be some fraction of that cross-sectional area because a lot of the cross-section is going to be solid. It's not going to be holes, and groundwater is only moving through the holes. Okay, so this is the device that Darcy, who was an engineer who worked in France in the middle 1800s, used to derive the so-called Darcy's law. I mean, he didn't call it Darcy's law. I think other people recognized how important this was and called it Darcy's law. So basically, he had a pipe filled with sand and water was moving at a constant volumetric flow rate or discharge rate, Q, down this pipe from high hydraulic head to low hydraulic head. So the hydraulic gradient here is delta H, H2 minus H1, divided by L or delta L, the distance here. And so if you divide Q by the cross-sectional area for this pipe, it would be a circular cross-section, then you get that little Q term, the specific discharge of the groundwater flux, and that equals the hydraulic conductivity of this material times the hydraulic gradient. And so these manometers here, these standpipes in this laboratory column, are like wells along the groundwater flow path. And this is written in a one-dimensional form here. Groundwater flow is not exactly horizontal, it's not exactly vertical, it's on an angle, but we're assuming that it's one-dimensional. But again, in the real world, groundwater flow is not just in 1D, groundwater flow is in 3D. So you can actually write a 3D form in differential calculus notation for Darcy's law. I'm just presenting the simple form. So again, how does groundwater move? Well, it moves from the recharge zone where water infiltrates from the surface. Again, we'll talk about that tomorrow when we talk about groundwater recharge. In high areas, we talk about groundwater flowing downward, moving largely vertically down to the water table, or water infiltrates and becomes groundwater. And then as I said, in unconfined aquifers, we can think of the hydraulic gradient as being kind of the slope on the water table. And in turn, that water table is what we call a subdued replica of the land surface. So if it's a hill slope, the water table is also sloped, but it's not as steep as the hill is. We also assume that topographic divides tend to be groundwater divides. So we can talk about a groundwater basin by comparison with a watershed or a surface water drainage basin. And often the topographic slope is what is driving the groundwater flow, but sometimes you can have subsurface flow from one surface drainage basin to another. And I'll talk more about that tomorrow and how that happens. So finally, the groundwater that is moving goes to the discharge zone. It exits to the surface. And as I mentioned, in the discharge zone in low areas, groundwater can flow upward as fluid pressure overcomes gravity. So again, in terms of mapping groundwater flow, like I said, hydraulic head in the real world varies in 3 dimensions. It also can vary in time seasonally. I'll talk a little bit about that tomorrow as well. When I talk about recharge, I'll talk about seasonal fluctuations in water levels. But let's not worry about that for right now. Let's just say hydraulic head varies in space. When you contour hydraulic head, you are inherently projecting a 3D field onto a 2D plane. And so you can do this in 2 ways. You can either do it in cross section, the XZ plane, horizontal and vertical, where you're looking at a slice through the earth, kind of like the way the water cycle is often drawn. You see it in a cross-section view, or you can do it in map view, where you're looking at it in the horizontal XY plane. But in either case, you have to remember that you are doing a 2D projection of a 3D field. And so inherently, there's going to be some simplification, and you want to minimize the error when you're mapping either in top-down view or in cross-section view your hydraulic heads. And so if you're doing a cross-section, for a hydrogeologic cross-section, if you can, it's best to draw that cross-section parallel to the mean direction of groundwater flow. So flow is either vertical or horizontal, but it's not into or out of the plane of the cross-section. So this is a simplified example. This is one of the well-known diagrams from hydrogeology, originally from a paper by M. King Hubbard in 1940, that shows a hypothetical groundwater basin. And so you can see the curvature of land surface. This almost looks sinusoidal. And you see that the water table is not quite as steep as the land surface is, but the divide at the surface corresponds with the divide in the groundwater basin. So to the left of this divide, flow is to the left in the subsurface, as well as on the surface. To the right, flow is to the right in the subsurface, as well as on the surface. The recharge area represents the entire area where flow is directed downward and groundwater has been recharged by infiltration. The discharge area is where flow is at least partly directed upward and groundwater is exiting at the surface. And this is often a valley bottom. Again, we'll talk more about recharge and discharge relationships tomorrow. These flow lines tend to be curvilinear. So they're intersecting the water table obliquely. They intersect the equipotential lines, or the lines of equal hydraulic head, at right angles. And that's a simplification. You get a right angle intersection between the flow line and the equipotential if you assume isotropic conditions. And so we typically, when we're contouring, assume isotropic conditions. And then finally, the divide and the bottom boundary, and then the valley bottom, tend to be conceived as a flow line as well. And these are what we call no flow boundaries. We're assuming there is not flow beneath the divide. We're assuming that flow does not cross under the stream. And we're assuming that this is a perfectly impermeable bottom boundary. But we know all of these assumptions can be relaxed somewhat in the real world. And finally, if you look at this and you're familiar with, for example, potential field diagrams from physics, like in electricity and magnetism, this looks like a potential field diagram. And in fact, Darcy's law is physically analogous to Ohm's law for the movement of electric current. We're just talking about the movement of groundwater or fluid through porous media instead. So this is what a water table map looks like. This is from an area where I worked back in the 1990s in Northwest Texas in the United States. This is the High Plains Aquifer, which is the largest aquifer in the United States by area. It covers parts of, I believe, 9 states. This is the southern part in the southern High Plains in Texas. These contour lines represent equipotentials on the water table. And these are actually in feet, not meters above sea level. So you divide through by like 3.25 to convert this to meters. But if we were to draw the flow lines, we would assume the flow lines are perpendicular to the equipotentials and that they're moving primarily from the northwest to the southeast. And that's following the slope of the land surface. And then at the edge of the escarpment, the eastern edge, this is kind of a cliff face here where you can have relief up to 250 meters. Then you see the equipotentials of the aquifers that exist on the plains to the east. So in terms of mapping groundwater flow, as I said, we assume that the flow lines are perpendicular to the equipotential lines or the hydraulic head contours. And again, the underlying assumption there is that you have isotropic conditions, that the hydraulic conductivity at any point is the same in all 3 directions, although you can assume that the hydraulic conductivity varies between points. In a system that is both homogeneous and isotropic, the grid of flow lines and equipotentials gives squares. That is, if you assume that your hydraulic conductivity is constant in space. Realistically, these squares are curvilinear. They're not strictly squares. They're deformed but proportional, as shown in this diagram from Hubbard. So these are deformed squares. So also when you map groundwater flow, again, think about it by analogy with Ohm's law with electric current. The flow lines can't cross the other flow lines. That would be like a short circuit. And the equipotentials can't cross the other equipotentials. Flow lines can converge. They can come together. So again, going back up to the diagram from Hubbard, you see the flow lines converging in the discharge area, but they can't cross. Relatively impermeable stratigraphic contacts represent no flow boundaries, which are parallel to flow lines. So a stratigraphic contact is like between 2 different layers of rock or sediment. So this is what we're talking about, this bottom boundary here with a relatively impermeable contact. So this might be in the real world like a really tight clay. And finally, when you're talking about the shore of a large body of water, either a lake or a sea, we typically define that shoreline as an equipotential line or a constant head boundary. So you can have a no flow boundary where there's no flow across it. You can have a constant head boundary where the head is the same all the way along it. Now, the water table, going back to Hubbard's diagram, is neither a flow line nor an equipotential because the hydraulic head varies along the water table. Okay, so finally then, just some terminology. When we have a contour map of hydraulic head in a single aquifer and it is a confined aquifer, we actually call that a potentiometric surface map. So if you remember that diagram that I showed previously from the National Groundwater Association with the different types of aquifers, they had the potentiometric surface. And that's just a projection of the level to which water rises in wells that are penetrating a confined aquifer under artesian conditions. Conversely, if you're contouring the hydraulic head in an unconfined aquifer, that's a water table map. So the map that I showed of the High Plains aquifer is a water table map. If you are mapping, again, in a top-down view, and you're mapping the direction of groundwater flow, like I was sort of drawing in with my cursor where the flow lines would be on the water table map, you are inherently inferring or assuming that the vertical flow is negligible relative to the horizontal flow. But the take-home message really is, if you're contouring, you need to know the depths of your wells and the aquifers that you're located in, because in a cross-section view, you can contour flow in different aquifers, but in map view, you want to represent only one aquifer. Okay, let me talk a little bit then about groundwater pumping. When you pump an unconfined aquifer, you are lowering the water table. And this depends mainly on the specific yield, which is abbreviated capital S with a Y subscript. And this represents the drainable porosity. In contrast, when you're pumping a confined aquifer, you're actually reducing the artesian pressure, lowering the potentiometric surface. And so when you pump a confined aquifer, the way you get water out is not by desaturation, it's by a little bit depressurization, because the water expands a little bit when it comes up from depth, but mostly it's by physically deforming the porous medium. As you depressurize the porous medium, you cause it to rearrange. And that can result in land subsidence. And I know land subsidence is a major issue in parts of Java, particularly around Jakarta. In either case, whether you're pumping an unconfined aquifer or a confined aquifer, you are lowering the hydraulic heads in the wells that penetrate that aquifer. And so you cause what's called a cone of depression, either in the water table or the potentiometric surface. And finally, we can define the difference between the initial pre-pumping head, and I need to fix this. This should be H0 minus H, not H minus H0. But the drawdown is the difference between the initial head and the hydraulic head at some point after pumping has started. So these are just block diagrams showing conceptually the cone of depression in the water table and the cone of depression in the potentiometric surface. So you're pumping an unconfined aquifer at the left or confined aquifer at the right. And this is what a map of a potentiometric surface looks like in a confined aquifer that is being pumped. This is in the states of Virginia and North Carolina. So Washington, D.C. is several hundred kilometers north. This is along the Atlantic Ocean. And if you look, you can see this line that's dashed that says 0. Well, before pumping, this 0 line, at least in a shallow aquifer, would have corresponded to the shoreline, would have corresponded to sea level. What pumping has done is it has lowered the water level in the confined aquifer below not just the land surface, but below sea level locally. So you can see elevations here as low as 160 meters. I'm sorry. I think this is actually feet, 160 feet. So about 50 meters below sea level. And so instead of flow being directed toward the regional base level, which is these rivers and Chesapeake Bay and the Atlantic Ocean, flow in this confined aquifer is being reversed toward these pumping centers. You can see these circles or bullseyes at the top and in the middle and at the lower right. These represent major areas of industrial pumping. And this is from a deep aquifer. So even though the water level is perhaps 50 meters below sea level, it is still above the top of that aquifer, but you are reducing the hydraulic gradient. So instead of the flow of that confined aquifer ultimately being toward the ocean, you are potentially causing seawater to flow toward these wells. It may take a long time, but again, I know in coastal areas like Jakarta, that's of concern as well. And I know we're getting close to time. We've got about 3 minutes left. I'm almost finished here. So let me do that. So if you're pumping a confined aquifer, the ideal response to pumping is nonlinear. You can see this is a log-log graph, and this drawdown, or the difference between the initial hydraulic head and the hydraulic head at some point in time after pumping increases asymptotically with time. We can define a parameter called transmissivity, which is just the product of the hydraulic conductivity times the thickness of the aquifer. We define that thickness as B. And so hydraulic conductivity is dimensions of length per time, the thickness is dimensions of length. So transmissivity is dimensions of length squared per time. We can also define storativity, which is the ratio of the volume of water that's pumped divided by the head drop in the aquifer times the cross-sectional area over which that pumping is occurring. In a confined aquifer, the drawdown depends non-linearly on transmissivity and storativity. In an unconfined aquifer, it depends on transmissivity and specific yield. So because you're physically desaturating an unconfined aquifer, you are withdrawing a much larger volume of water than if you're simply depressurizing a confined aquifer. So when you pump a confined aquifer, ideally, you're getting water out of storage in that confined aquifer. But in fact, in the real world case, we know confining layers can leak or they can be discontinuous. And so water can come not only from the confined aquifer, but from the confining layer itself or across the confining layer from overlying aquifers, especially if that confining layer is not continuous. So this has implications for land subsidence. If you're pumping the confined aquifer, the hydraulic head, the potentiometric surface can decrease relatively rapidly. It doesn't immediately propagate into the overlying confining layer, but if the hydraulic head in that confined aquifer becomes less than the hydraulic head in the confining layer, so that the aquifer is no longer artesian, that confining layer drains. And in any case, the consolidation of the confining layer itself tends to be the main cause of land subsidence, because typically confining layers are clay and they deform plastically much more. You can squeeze them, you can squish them much more than the aquifer. And so in that process, the clay particles are reoriented and you permanently lose pore volume. So I'll end with this slide. It is right at 1:30. And these are maps of the change in the water level in the deep confined aquifer system from 1860 to 1961 in Central California. And then the land subsidence from 1926 to 1970. You can see how much land subsidence is noted by where the land surface was by the dates on these telephone poles. This is one of the most famous photographs in American hydrogeology, 9 meters of land subsidence between 1925 and 1977. And if you're talking about land subsidence of even a meter in a place like Jakarta in a coastal setting, coupled with sea level rise, then you're going to have inundation. So I will stop there. I'm pretty much on time. And I'll be happy to take any questions by email. Judfun has my email, or if you have questions you think about and you want to talk about them tomorrow, that's fine too. And I will send Judfun my notes for tomorrow. Thank you, everybody, for your attention.
Okay, thank you, Professor Alan. Is there any question? Professor Alan, can we have some question, maybe 3
Absolutely.
questions?
Oh, even more. I have plenty of
Okay.
time here. I'm sorry, I didn't allow enough time for questions. It was like driving a bus. I was so busy on finishing my bus route. So yes, please, if you have any questions, I will stay on. Feel free to ask the questions.
Please, everyone, if you have question, you can
May I,
directly.
just one.
Please, Pak Dadi.
Thank you very much, Mr. Zatwan, for this kind of opportunity. Sorry. Prof. Alan, my all due respect to from Alan, Prof. Alan Fryar is very welcome to you, though it's online welcome to our department. And thank you very much for a very nice presentation about groundwater. It's such a great knowledge for us. And as we know that groundwater is one of the process in hydrologic cycle, and it's take essential and significant role in maintaining water balance in our river basin. And it sustains the availability of river water, particularly in dry season period. And hence we need to preserve it by doing conservation activity. I have a question, and is it possible to have a good estimating regarding how much volume of groundwater that comes from rainfall that falls over recharge area? And because you explained about recharge area, that's very interesting for me, because I think I really want to know about the method to estimate the volume of groundwater that comes from rainfall that falls over recharge area. Probably you have some experiences regarding what method we can employ to estimate the amount of rain that convert into groundwater, since that's very essential to us for assessing effectiveness of our vegetation conservation activity to control flood, erosion, and landslide events in a basin or watershed.
Yes, I can. I will talk some about that tomorrow, but okay. Because there is so much to cover. Even my talk tomorrow, I was going to talk more about principles. Perhaps I can talk some more about techniques as well. But of course, one of the ways of estimating that volume is just a simple mass balance. If you look at the rise in water level in wells that are not being pumped, for example, during the rainy season, or if you are looking at an area where there is irrigated agriculture, perhaps not paddy, but other agriculture where there is what we call return flow, where there is infiltration of the irrigated water, the amount of water that is being added either during the rainy season or artificially gives a, I guess, kind of a minimum estimate, at least, of the storage capacity that is available. Now, it's possible, in fact, it's likely that the volume of groundwater that is available is going to be greater than that estimate. But at least that gives you an estimate of kind of the minimum volume that is replenished, particularly if you were just talking about rainfall, if you're not talking about artificial recharge. That gives you an estimate of the minimum volume that is replenished during each rainy season. One of the things that we need to think about is environmental needs for groundwater as well. So one of the common assumptions when we talk about the amount of available groundwater is that the volume of groundwater that can be extracted is equal to the recharge volume. That's the sustainable amount of groundwater withdrawal. But that doesn't account for the fact that some of that recharge is needed to maintain environmental flows of rivers, for example, not only for ecosystems, but also for downstream users. If downstream users are using surface water, some of that surface water is going to be contributed, as I'll talk tomorrow, by groundwater discharge. And so you can't simply say, or it's not sustainable to say that the available volume of water to be sustainably withdrawn equals the recharge, because some of that recharge is potentially needed for other purposes. Pakdani, does that answer your question?
Yes, so thank you very much. Can't wait to see you tomorrow.
Okay, thank you. Again, I realize I am running over. If this were my class, my students would be anxious to go, but if there are any other questions, I will be happy to answer.
Can I have some question too?
Oh, of course.
Because in Indonesia, we have some problem regarding land subsidence pollution. In Jakarta, it sinking about maybe 1 meter every year. And we have another problem in Semarang, in central of Java. It already sinking below from sea level, maybe around 2 meters below. And if any technique or approachment to recharge the groundwater regarding exploration, Professor Alan, because sometimes we pump groundwater from catchment, and but is that possible to us to recharge again the groundwater level? Because we must balance inflow and outflow, right?
Yeah.
If we took the water maybe around 3 meter cubic per second, maybe how we can infiltrate or recharge the level of groundwater with the same amount of water. Is that possible to us to doing
It's
that?
difficult because you have to have the storage volume available in the pore space, in the subsurface for groundwater that is being recharged. And as I mentioned in the last couple of slides, often land subsidence is an irreversible process that you are losing the volume because of compaction. And so really the best thing to do is to if possible, maintain artificial recharge, but recognize that you're not going to lift the land surface back up. You are simply going to you're going to stop the land surface from going farther down. That's what happened in California, for example. They realized that they couldn't, recover 9 meters of land surface elevation. They could simply keep it from going farther because it was causing, as I'm sure it happens in Indonesia, significant infrastructure damage. Roads buckle, canals break, pipes break. So that is a real problem. So it's more a matter of stopping it from getting any worse. And part of the problem in California is, as you may know, because of the fires that are happening in California right now, there is a serious drought. And so starting in the 1970s, really, there was a real move to use surface water instead of groundwater to limit land subsidence. But when the drought happened, the farmers said, the heck with that, we're going to start pumping again because we need to be able to water our crops. And so land subsidence started again. And so part of it is not just the physics or the science, it's really the management in terms of how do you incentivize people to conserve water? How do you find alternate water sources to keep the problem from getting worse?
Yeah, because I think land subsidence is more common in Asia because groundwater extraction is become massive right now.
And in a lot of places, not just Indonesia, but parts of the United States, Thailand, China, it's not regulated in the same way. And so, anybody who can afford to put in a well puts in a well. And then, if everybody is pumping, it's like having a bunch of straws in the glass, and it's everybody's sucking and the water level goes down. So that's a management challenge very much. But we have to have good science to support good management. So the question previously about estimating groundwater recharge, you have to have some sort of way of getting a good estimate of recharge and a good estimate of discharge, how much water is actually being pumped.
Okay, thank you for your explanation.
Oh, you're welcome. Are there any other questions?
Any other question?
I will be happy,
Can
like I said, to
asking.
Please.
Sure.
Okay, Thank you for the opportunity to me to asking Alan. Good evening, and I'm interested about you when you explain type of aquifer. You explain it that we have unconfined, confined, and then liquid aquifer and tertiary aquifer. I'm wondering, based on your experience, Professor Alan, is it possible to find a multiple aquifer in one area?
Absolutely.
Is it possible to find aquifer in one area? And then the second question, based on the mapping of groundwater that you showed before, because some of the journal that I read it, I wondering what difference between the gaining stream and the losing stream that usually we can read from that groundwater mapping and from the water table contours phi or the opposite of phi, and the indicate for the gaining stream and losing stream. Thank you very much.
You're welcome. So yes, in some areas, it is possible to find multiple aquifers. Typically, perched aquifers are not major water supplies. They may be important for ecological purposes or maybe for small wells or springs. But depending upon the local geology, you can have an unconfined aquifer and multiple confined aquifers stacked on top of each other, like a layer cake, water table or unconfined aquifer, first confining layer, then your top confined aquifer, then another confining layer, and then your next confined aquifer. So for example, that potentiometric surface map I showed with the pumping centers, that was like the third confined aquifer down. And so really, whether it is practical to try to pump from a deeper aquifer depends upon how deep, how expensive is it to drill in that area. It may be more expensive to drill into a hard rock aquifer like a basalt aquifer than it is to drill into sand or gravel. On the other hand, the deeper aquifer may have cleaner water, whereas the shallower aquifer may be polluted. I mean, if I lived in Jakarta, I wouldn't want to drink from the water table aquifer. It's probably contaminated. There's probably seawater intrusion. So yes, there can be multiple aquifers, and whether it is practical to try to pump from different aquifers really depends upon how productive they are, how deep they are. So for a farmer, for example, that farmer may not be able to afford to drill to like the second or the third aquifer unless he or she is producing a really valuable crop. In terms of gaining and losing streams, stay tuned for tomorrow. We will talk about gaining and losing streams tomorrow.
All right. Okay. Thank you for the explanation. All right. We'll see you tomorrow, Prof. Alan. Thank you.
Okay.
Unfortunately, Professor Alan, I think time is up for today because
you guys have other things to do. I know.
Yes,
it's 8:45 your time.
Yeah, but some of students must continue their class for another lecture.
Of course, and I appreciate your patience. I will allow more time for questions tomorrow. I apologize, and terima kasih, and I will see everyone tomorrow at 7 o'clock in the morning your time. And Jodhan, I will send you the PDF of my slides for tomorrow.
Yeah, I already sent to the student about regarding your presentation today, and maybe for tomorrow is continue